So it will be just 1 second here while I start to share my screen so that everybody can get a look at my presentation. And also, I want to share a link to my presentation so everyone can follow along. There is alt text on all of the images as well as some of the notes for the things I'm going to talk in case audio visual processing is something like for me is not always the easiest thing for you to do. So once again, I'm using Cadre to support large-scale bibliometric studies. My name is Samuel Hansen. My pronouns are they, them. I am the mathematics and statistics librarian at the University of Michigan. And more important for this talk today, I am one of the Cadre Research Fellows. And I will talk a little bit more about Cadre now. So the question, of course, is what is Cadre? So Cadre stands for the Collaborative Archive and Data Research Environment. Second here, I need to find my speaker notes. Okay. And it is a gateway to standardized text and data mining services for very large data sets. I'm talking very large data sets. It's funded by the Institute for Museum and Library Studies and is built by the Indiana University Libraries and Network Science Institute, as well as the Big Ten Academic Alliance, which is mostly Big Ten schools in the United States. And it's supported by the Midwest, South, and West Big Data Hubs, Microsoft Research, and Claravit Analytics, the people who put out Web of Science. So for the data access within Cadre, right now there are multiple bibliometric data sets and they are all processed into PostgreSQL databases. There's over 220 million articles, and that should read over 1.7 billion citations in these data sets. There is a GUI query builder as well as direct SQL access via virtual desktop if you are one of the people who are working directly with Cadre. This is not something that anybody in here can necessarily do, but if you want to work with them, they can set that up for you. And everyone can actually access the GUI as long as you have a Google login of some sort. For their computing, because they also offer a computing backend. Right now, they have Jupyter notebooks, and they can also run custom scripts directly at Indiana University. In the future, they do hope to integrate Apache Spark, Docker, Hadoop, many more big data computing technologies directly within the platform. And they also have a big focus on reproducibility. So they have a sharing marketplace built directly into Cadre. They will share code, they will share data, you can share tools so that people can reproduce your research. This is something that could be really big, especially if there is this whole computing platform behind it. And so this is their future planning diagram. And so there's going to be authentication, authorization. There's already some authentication and authorization built in. And so you can set up like projects, teams, and so forth. There's already the database. In the future, there's going to be APIs, so you can more directly on the back end access some of these. You can see all of the different infrastructures they want to integrate in. They do already have a few of those graph databases built out for the citation networks. And they want to build out more storage infrastructure. So if you are an institutional Cadre member, you will have institutional storage for people who log in with your authentication systems, and also local storage for people to upload their own data sets. So that's in the future. Some of this is built, not all of it. It was only started in 2019. So what data is in Cadre right now? So the Microsoft Academic Graph is in Cadre. So this is around 208 million documents, 1.4 billion citations, and it's an open bibliometric data set. Everyone can access this. Everyone can do searches on this. Patents from the US Patent and Trademark Office, around 9 million patent application documents. All of those are openly accessible. Web of Science. We all know Web of Science. It's a lot of papers, 1.7 billion citations. This is not openly accessible. You would have to be a member of one of the universities that subscribes to the XML of Web of Science. This is mostly Big Ten universities that have direct access through Cadre right now, but there are a few others. And you can work with Cadre and Claravit to set up everyone at your university being able to log in and access that. And there's also the COVID-19 Open Research Dataset, and this is tens of thousands of scholarly articles about our recent pandemic that you can access that. I believe is on the back end and not on the front end. So how do you access Cadre? So there is the Cadre gateway. If you are following along with the presentation that I linked to, there is a link. It's cadre.iu.edu and then /gateway. And then how do you access Cadre in a different way? The not openly accessible virtual desktop that I mentioned earlier. And that's if you work directly with Cadre. So if you go to that website, you should see something a little bit like this. So up in that top right-hand corner, there is a login button. When you log in, it'll ask you if you want to use Google or CI login. So CI login allows you to log in via your university. And so that's what I chose in the second screenshot here. You can see I just search Michigan and University of Michigan is down there. That's what I would log in through. And that gives me access to also Web of Science when I am doing this. So these are sort of the choice. You can just do Google, as I said. And then you will be here on the dashboard. And so you can see there's the query builder. So that's the GUI way to search these databases, data sets. There's the Jupyter Notebook. So that's how you start doing some computing on your results of your searches. And then you can also see the marketplace. There's that featured package. And so these are already pre-built data sets and scripts that you can run to reproduce data or to use on a different set of data if you really like their analysis, but you wanted to apply it to your area. And so then if you click on Query Builder, you will have your choice. If you don't have Web of Science access, that just won't show up. I'm just going to walk through here with Microsoft Academic Graph because it's what everyone will have access to. And so then you will just end up somewhere that looks like a normal library advanced search. So it's the image on the left there. So there's a pop down for what things you want to search. You can search year, DOI, journal name, conference name, author name, and the title of the article. And you can add multiple fields as your normal advanced search. And so then below that, you see what you have output. And then on the right, you see all the possibilities. There's a lot of different bits of data that you can ask them to output. Not all of it's chosen because, say, author sequence number, not really that useful to everybody. And it will pump back arrays of names of authors if there's more than one author. So those are the things that can happen here. And so then you can also choose if you want to include the citation network graph or the reference network graph of the articles that come back. There is a limitation of 10,000 items in that graph just to deal with processing capabilities. If you need more than that, you can work directly with Cadre to get it. But just on this sort of thing that everyone has access to, there does need to be some limiting on how much we hit their processors. And so then you'll hit search and it will say processing and it will be done. And then you go to the Jupyter Notebook and you can get brought out to your query results folder. And so here is just, I think I did Journal of Information Science or something similar to that. And it pumped out a ton of results. And you can see it's just in a CSV. So if you want to work with it on your own computer, you can just directly download it. But you can also work with it directly in Jupyter Notebook. So here's a quick Python script that I just whipped up that just prints out the items field by field. And so you can do, of course, much more analysis with this because Python is a Turing-complete computer language, so it can do everything as long as you know how to write it. You can also use R directly in Jupyter Notebooks. So that's sort of the working with results, how to get results. And I also want to talk a little bit about how you can work directly with Cadre. So you can work with Cadre if you have something that you need that is beyond the capability of that query builder. And they have pulled it out. You can see for a bunch of these, they have just pulled them out, put them on GitHub so people can grab them. And these were mostly for things with the Cadre Fellows that I'd mentioned earlier. So the Cadre Fellows were 8 bibliometric fellowship teams and then 4 research cohort for the study of coronavirus teams started at the beginning of the pandemic. There's a bunch of Cadre Fellows webinars where people have talked about their work. I have done one, actually I've done 2 of those. And so you can definitely go look at those. You can read more about their stuff there. I'm just going to toss up a few example projects here that you can glance through really quickly. So these are things like science maps for COVID-19 articles, citation impact through egocentric centered networking, the impact of like air links. So these are direct like airport links on collaboration. Like if two cities have direct airline flights, are they more likely to be collaborative? Like there's people who've done some really interesting studies here. And so that's sort of the first half. I know I flew through that. Now I'm going to fly through a bunch of the stuff I've done with Cadre to give you a sense of what you can really do when you have access to this much data. And so my two fellowship projects are comparative analysis of legacy and emerging journals in mathematical biology, and systematic overtime study of the similarities and differences in research across mathematics and the sciences. Might notice a little bit of a tie-in here. Yeah, they're all math things. I love math. I will always love math, and I will continue to study math even while I'm in the library space. So first up, I'm going to talk about those mathematical biology journals. And so what we're looking at is these 4 legacy journals: Bulletin of Mathematical Biology, Journal of Theoretical Biology, Journal of Mathematical Bulletin of Mathematical Biology, Mathematical Biosciences, and these 2 new journals that publish a lot of mathematical biology paper but are not directly math bio journals. That's PLOS Computational Biology and Journal of the Royal Society Interface. And so we studied across 3 data sets. So this is Web of Science, Microsoft Academic Graph, and PubMed. And we managed to match 18,300 articles for the time frame we were looking at, which was 2003 to 2017. And that was 99.23% of the articles in the smallest of the data sets, which was Web of Science. So we did have incredibly high matching across these data sets, which is really, really good considering a bunch of them did not have DOIs across all data sets. And so we focused on citations, organizational citing organizations, author organizations, and citing journals. As well as indexing terms. We use Web of Science for the former, and for the indexing terms, that's where we use the Academic Graph and PubMed. Now, I'm going to just glance through some of these because you're going to notice something pretty quickly. And so journal impact factor, I know it's not good. Not a great metric, but it's what a lot of people use. So we wanted to use that and then compare it with median citations to see if it would give us the same result, to see the impact that outliers would have, because if it really impacts GIF, then it wouldn't impact median citations as much. But you will notice PLOS is on top, then Interface, and then a big cluster of math bio journals. It's true for across all of them. Median citation with the 2-year window, median citation total, journal impact factor, which has a 2-year window. All of them are pretty much the same, with the Journal of Mathematical Biology having a spike in the late aughts. It's the same across them. And then looking at the overlap of the citing journals, you will notice here again, the traditional, the legacy math bio journals cluster a lot. And there's a lot less overlap with Interface and Comp Bio. With the sort of the middle ground is Journal of Theoretical Biology. And that is largely because that one is a little bit less directly math bio. So there are differences here. And the thing is, as I said, you'll notice something. These differences are pretty much the same across all of our analyses. We keep on seeing the same thing, and it's what we expect. And there's nothing wrong with what you expect showing up, but there really wasn't that much super surprising in this, with the exception that we managed to see, before it was actually announced, a major citation ring that just sort of showed up in our analysis, surprisingly, because then 1 week after we saw it, it was announced that there was this big issue. And so then looking at the fields of study, which is the indexing term in Microsoft Academic Graph, there was not that much uniqueness along the traditional ones, and a lot more uniqueness along Comp Bio and Interface, and that is because they do publish in a much wider range. So we saw something that we really expected here, but it's not that surprising. So let's move on to things where I might be able to surprise you, might be what you expect, but it'll still be a bit surprising. And that's some of the things I've done looking at citation aging. So I analyzed all the articles in the entirety of Web of Science from 1900 to 2017, all of them. I used the 252 Web of Science categories to limit them. They are journal level, not article level, but we are looking at, 55 million articles in here or more. So, you know what? It's coarse, but at that scale, I'm okay with it. And let me just say, this is just incredibly overwhelming. It's that. That's the median citation age. Anyone able to get anything from that? I mean, other than older papers have an older median citation age. So I decided, looking at everything at once, maybe not my best plan ever. So instead, I used only the sciences. And I spun them up into astronomy, biology, chemistry, mathematics, and physics. Now, these are not mutually exclusive. So articles could be classified in something that spins into physics as well as something that spins into chemistry, or that spins into chemistry and biology and mathematics. But there won't be double counting issues because they're spinning into different things. It doesn't need to be mutually exclusive. So with this focus, instead, we're only going to have 5 lines on our graphs. So here is the median citation age for these disciplines from 1900 to 2017. You'll notice the orange one here is math. There's a pretty big gap there between math and the others. And then you have physics and astronomy sort of clustered together, then chemistry, and then bio. Bio doesn't like old papers. Just doesn't. Mathematics, on the other hand, really likes old papers. For example, this. So this is a graph of the year that the median oldest citation was made. And if you notice, math is almost a line. The median oldest citation across all of these is made in about 2007. So across all of the citations in 1905, the median oldest, so half of the papers half of the citations have been made since 2007 in mathematics. And astronomy also likes old stuff, not as much as math, but it does. And then there's a big drop. There's a legitimately big drop down to the other disciplines. Again, biology is at the bottom, but this time physics actually drops below chemistry. So you do see some change there, but math is consistently the oldest. If we look at percentage of citations over 5 years old, when you go back to 1900, they're all pretty much the same. But then when you get to the mid-century ones, math just stays up there. It's like, oh no, this is steady. We're going to keep on looking at everything while everything else drops. 15 years, that's even more distinct. It really is. And then 30 years. Again, we see how little bio cares about old citations. Don't like old papers in biology. Poor old papers. Math, again, really likes them. There's 4 single years that astronomy, for some odd reason, spikes up and then goes way down below it. So that's just straight up citation aging. Now I'm going to talk about awoken papers. These have traditionally been referred to as sleeping beauties, a name that I'm not going to use because it's incredibly problematic. I mean, there's gendered implications. I mean, people refer to the papers that wake them up as Prince Charming. No. Let's not do this. And also, it's incredibly excluding because there are a majority of people in the world that did not grow up with Eurocentric fairy tales. And to call something a sleeping beauty is to focus on that and exclude them. So I call them awoken papers. I use the Key-Ferrara-Radici and Flamini coefficient from 2015. They did this on 1900 to 2014. I'm doing it to 2017, but I'm not only analyzing the raw awoken paper counts, but also the ratios and the impact of citation numbers. So there are some differences. And so here, these are the 2 left-hand columns are the raw counts. If you notice, there's not much difference between the ones I did, which is in the middle and on the right. So the middle one and the one on the left, really physics and chemistry multidisciplinary switch positions, and medicine general internal hops on, surgery falls off. But chemistry multidisciplinary has a ton of papers in it. And by not doing ratios, we're not field normalizing at all. So for the ratio, that's the number of awoken papers divided by the total number of papers. And you notice here, that is a lot different. You have physics multidisciplinary stays on, drops down to 3. Mathematics is still on at position 4, but 1 and 2, those are completely new. And you notice there's a lot more mathematics on this list, and a couple of social sciences. You have psychology, anthropology, and so now I'd like to point out what happens if you only look at papers with 25 citations or more. These are all ratios: 25, 100, 300, or 500 citations. I did have to limit them because otherwise you have a ton of outliers for disciplines that have very few papers with that number of citations. And so I list how I limited them for all of them. It's 85th percentile, 80th percentile, 75th percentile, and 70th percentile. And mathematics, my love, mathematics stays on top for all of them. And a lot of these are not actually close. Some of these are like double the ratio. There's very specific numbers in the notes, but you notice a lot of these are mathematical. You have stats, you have multiple math methods, you have operations research as well. There's some engineering and social sciences too. And so these can really change how we have looked at these awoken papers, which have been thought of as interdisciplinary and sciencey, but there's a lot of social science here, and just how important mathematics is for older papers, and what that says about the nature of mathematical knowledge, which I can talk a lot about, but I'm already over time. So instead, I will pump it over to questions.
Thank you very much, Sam. This was an absolutely fascinating presentation. I'm sure my colleagues are still pondering over the questions. So what do you think, Steve?
Yes, I can't see any arriving in the QA at the moment. I was just fascinated, Sam, by the scale of the Cadre operation having access to, as you say, billions of data points and being able to do this kind of analysis.
Yeah, it's really interesting. So like most of these assets are way too big to work on in Jupyter Notebook. So I do a lot of this on my computer, of which I had to build a new one in order to actually handle some of this. I look at regularly gig to nearly terabyte size files while I'm handling these sorts of data sets. But it really is interesting to be able to take these really big over time looks, where instead of trying to look at just journal numbers or specific articles or people, like I'm getting to look at disciplines and how they change over time, and that to me is really fascinating. And so I see there is a question from Jennifer in the Q&A. So how the data sets were selected. So I don't know why PubMed was not selected. I can tell you why Google Scholar is not selected, and that is Google doesn't make any of that available. That's just a closed data set. They don't really work. It's also not that well developed on their end anyway. It's very much a black box. And so Microsoft makes the academic graph completely open. You can actually go download the full data set now yourself and do with it what you want, as long as you cite and do normal things like that. And Web of Science was used because the actual purchases of the XML predated Cadre. So I think in some ways I was not involved when the grant was written and it was originally come up with, of course. But I do think some of it was just trying to figure out how we can actually use this data set. So if you've ever seen those XML files, you know that they are difficult to work with. To say the least. They're quite interesting. And Kaylee, hey Kaylee, it's been a couple days since I spoke to you. Often undergraduate experience librarians are not subject librarians and may be steering students towards recent citations without the nuance of discussing how different citation patterns can be in specific fields. What do you think the bibliometrics and subject specialist librarian communities can do to communicate findings like this out to people directly teaching students foundational information literacy and library tools? That is a fascinating question, and something I think subject librarians, as well as the bibliometrics and scientometrics community, need to do a better job of, is to engage directly with these communities, the ones that do the teaching and write for their journals, go to their conferences. Like there's just not that much connection built up between those two communities, and I think that is at least the part where we can start. And so see another question from Linda. Practical level, I don't know. I don't know the costs. And is it resource intensive to ingest the updates? Not too much. That I can actually touch on. So they have scripts that can take in the XML that they have pre-written, and they have worked directly with Microsoft Research and Clairvit, who help build out these things. And Kate Nyhan asks, with this longitudinal citation info, you could presumably look at S-curves beyond just the shooting stars and awoken papers. Are you familiar with anyone using Cadre to study the shape of decay of citation curves? I am not familiar with anyone doing that. That was not one of the fellowship projects, but that is definitely something that would be fascinating to study. And if it's something you would be interested in studying, I would be more than happy to talk with you and either help you get set up with Cadre or maybe collaborate on it, because that sounds fascinating. I have the data to study that already.